Hello and welcome to Lessons in Logic video number 38, where we're going to be introduced to proofing. Before we do, I decided some time back, as long as I'm doing this and I have the logic on part of the screen and my face up on another corner of the screen, I should try to have something interesting under the face in the otherwise unused corner of the screen. So I started putting some, making some pictures visible there. But while I'm at it, why don't I just start off with the whole picture? This is Hong Kong. This is Kowloon for the most part. You can see a bit of Lantau Island and a bit of Hong Kong Island in the background, but most of this is Kowloon, viewed from Kowloon Peak. And I have crawled out very carefully on that magnificent rock because it's so cool. It's such a great rock. This rock on Kowloon Peak is just magnificent. Wonderful, wonderful location to hike to with extreme caution. Now let's talk about proofs. Now, in logic, we are generally studying methods to determine whether the premises of an argument provide good enough support for their conclusion. Proofs are not like that. Proofs are the exception. In proofs, what we're actually doing is demonstrating that the premises of an argument provide adequate support for their conclusion. In this case, that the premises of the argument guarantee the conclusion. In other words, we're proving that arguments are valid. That's what we do with proofs. We take an argument that your logic teacher has already told you is valid, and then you prove that it's valid. You prove that the premises guaranteed, 100% guarantee the conclusion. So it's not possible for the premises to be true and the conclusion false at the same time. Maybe the conclusion is false, but if so, one of the premises must be false as well. All right. Now, this does mean we might want to reconsider our definition of logic. Is logic the study of methods for determining whether the premises of an argument provide good enough support for their conclusion? And does that mean proving is not part of logic, strictly speaking? Well, of course it's a part of logic, which means the definition must be a little fuzzy around the edges. It must be the study of methods plus some other related stuff like proving that the premises of an argument provide good enough support for the conclusion. I think that's fine. I think the close enough approach is fine. I'm sure I've said it to students before. At the moment, I'm thinking, however, maybe a better definition of logic would just be logic is the study of how sentences or how propositions. Logic is the study of how propositions support each other or fail to support each other. And we're certainly studying that every time we test arguments to see whether they're valid. We're certainly studying that when we prove an argument to be valid, and we're certainly studying that in inductive logic as well. Now, I say proofs are used to prove that an argument is valid, which is a fancy way of saying that you'll never be given a proof for an argument that's invalid. You can assume that if your logic teacher gives you a proof, the argument is valid, unless the teacher has made some terrible mistake. You won't be asked to do a proof on an invalid argument. Now, that's the norm. Actually, what we do with the particular kind of proof, the reductio ad absurdum proof strategy, is pretty much the same thing we do with an abbreviated truth table for a valid argument. And you can use the abbreviated truth table method to prove that an argument is invalid. So with some clever adjustments to the rules for proofing, you might be able to prove invalidity. Don't quote me on that. Wait for later. Maybe I'll make a video on it. I can't promise anything. All right. Let's stick with the norm. Let's stick with the usual approach. And if you are studying logic in a university logic class or something, I'm sure this is more than, I'm sure you don't need more than what we're doing here as far as the norm goes. Proofs are for valid arguments only. All right, so logic is blah, blah, blah. A valid argument is one in which the premises guarantee the conclusion. It's not possible for the premises to be true and the conclusion false at the same time. In deductive logic, we study validity and ways of testing for validity, or in this case, demonstrating validity. So for this and a few more videos, I'm not sure how many at this point, we are looking at ways of proving that an argument is valid. Like the truth table method, we're going to be using statement logic, where we use capital letters to stand for atomic statements. Atomic statements are the statements that are not made of any other statements. And in statement logic, we break an argument down into its parts, and specifically the parts we break it down into are the atomic statements, the statements not made of any other. So now let's give a definition of proofs. A proof is a series of steps that leads from the premises of an argument to its conclusion. Each step will appeal to an infallible rule, which means that unless you've made some terrible mistake in applying the rule, you will have demonstrated each step to be guaranteed by the premises. So you do that until you get to the conclusion, which is how you prove that the conclusion follows from the premises. Now, we're not proving conclusions of arguments to be true here. We are proving only that they are guaranteed by the premises. If the premises are true, the conclusion is true. So proofs prove that a conclusion to an argument follows from its premises, and there are various rules for proving. Now, this will vary in different textbooks. Look at that. What do you know? For some reason, my notes have moved from horseshoe to arrow. That's fine. Anytime you see an arrow, if you're accustomed to using the horseshoe symbol, use the horseshoe symbol instead, or just assume it means the same thing. So here we go. We could make this adjustment if we wanted to. But frankly, I would have, if I'd had the arrow handy or more presence of mind, I would have switched all my horseshoes to arrows videos back because I like working with the arrow better. Who wouldn't? But arrow and horseshoe mean the same thing. And if there's any subtle distinction, it's a matter for theoretical work far past this. This is Logic 101 stuff here. Horseshoe and arrow are totally the same as far as we're concerned. Okay, so what was I saying? Different textbooks will give you a different set of rules for proving. So there's infallible rules. Now, infallible rules are things like if it's true that if X and Y and X, then Y must be true. That's an infallible rule. There are lots of other infallible rules, like if it's true that if X, then Y, and also it's true that not Y, then not X must be true. This is an infallible rule. There's lots of infallible rules. And the more rules you have, the more flexibly you can apply them to different premises. But the more rules you have, the harder it is to keep track of them. So it's very similar to other things in logic. You have more things you can do, but more to remember in order to do those things. And also different authors of different logic textbooks might give you a different set of rules, not only because there's no one perfect way of having the ideal number of rules to keep track of, but to be able to apply usefully to different kinds of premises. But also because not everyone is necessarily going to agree on what is the ideal set of just 10 most important simple rules. Anyway, there are various infallible rules, and there's probably a whole lot of them, like hundreds of them, if not dramatically more than that. But keeping it simple, you want to have a small number of manageable, simple rules, but not too small. And so here is a good set of rules. And probably, if this is what's in my notes, then I'm using the rules from Copy's textbook, or I bet this isn't Copy. I bet I'm using rules. I bet I'm using the rules here from The Power of Logic by C. Stephen Lehman, and then Ryan Wasserman and the Howard Snyders. That's probably the set of rules we're working with here, but different rules, different textbooks, and it doesn't much matter. The important thing is know the rules you're working with. Here's a good illustration of a set of rules that can be used for proofing. So I'm talking too much about some of this stuff. A proof is a series of steps that leads from the premises of an argument to its conclusion. Each step will appeal to a rule, and these rules are completely trustworthy. So the rules come in different categories. And one category of rules is the inference rules. The inference rules are the rules that allow us to make inferences that are familiar, that are based on the famous forms that we study in statement logic. Now, what I just said may or may not have been a formal definition of inference rules, but it should work just fine. Please take it until you learn something better. So basically, what we do here is we take some of our famous forms and a couple of other ones that are similar enough, and maybe I really should give you a nice formal definition of what is an inference rule, but let's not bother yet. Maybe we won't bother at all. What we do is we take our famous forms like modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism, and constructive dilemma, and we formalize them. And this is indeed the formal version of modus ponens. I mean, this is modus ponens, actually. Well, this is a symbolic representation of modus ponens. Modus ponens is this relationship among statements. Statements that have this pattern. If P, then Q, P, therefore Q. Statements that have this pattern have the modus ponens pattern, and this is the pattern, and I'm repeating myself. I'm repeating myself. So I'll just stop repeating myself and hope I didn't lose track of anything important there. This is an inference. This is a famous form in statement logic, and you can use it anywhere. The point of having it here is when you have two premises that have this structure, P, if P, then Q, and P, if you have any premise that has an if-then structure, and then another premise that has the if clause of that other if-then premise, then you can conclude the then clause of that if-then premise. Simple enough, right? If x, then y, x, therefore y. That's all we're doing here. You find an if x, then y in a premise, and an x in a premise, you can conclude y. That's the rule. And if you can do that and do some other similar inferences, you can eventually get to the conclusion, depending on whether you have enough rules. At some point, you have to make sure you have enough rules. And our point will be probably in a subsequent video. All right, so modus tollens. That is to say, you want to have enough rules that you could definitely get from any set of premises to any conclusion that validly follows from them. Eventually, we'll have enough rules for that. So modus ponens is one of our 8 inference rules. Modus tollens is another one, if P, then Q. Pardon me for this horrible typo. If P, then Q, not Q, therefore not P. Hypothetical syllogism. If P, then Q, if Q, then R, therefore P, then R. And again, if you find something like this in the premises, this rule just means you're allowed to conclude it. You're allowed to appeal to the hypothetical syllogism rule to show that given your premises, if P, then Q, and if Q, then R, P, if P, then R, given your, let me start that sentence again. If you find in your premises, if P, then Q, and if Q, then R, then you're allowed to appeal to the hypothetical syllogism rule to show that if P, then R follows from your premises. And then we have disjunctive syllogism, if P, either P or Q, and then if not one, then definitely the other. Either P or Q, not P, therefore Q. Either P or Q, not Q, therefore P. And constructive dilemma, which again we know, either P or Q, if P, then R, if Q, then S, therefore either R or S. Now, here are a few that we have not met as famous forms. Simplification allows us to go from P and Q to just P, or P and Q to just Q. In other words, if you had a premise that said Mark has a teacup in his left hand and Mark has a piece of candy in his right hand, you could simplify that and say Mark has a piece of candy in his right hand and leave out the part about the teacup. If both of them are true, then either one of them is true by itself, is the idea here. Conjunction is simplification running backwards. If you have a statement that says Mark is holding a piece of candy in his right hand and a statement that says Mark is holding a piece of candy in his left hand, you can combine them and say, therefore, Mark is holding a piece of candy in his left hand and Mark is holding a piece of candy in his right hand and Mark is holding a teacup in his left hand. And addition, well, this might be a little subtler, but if P is true, then it's true that either P or Q. And if P is true, then it's Q that either, I should probably have it phrased this way. If Q is true, then it's true that either P or Q. The point being that any true statement, let me rephrase that. If a statement is true, then any disjunction that has that statement as one of its disjuncts is true. In other words, from any statement, you can go to an either-or statement where either the either or the or is that original statement. Let me try to say that a little more simply. If any statement is true, you can conclude that either that statement is true or something else is true. Now, these rules will allow you to make all kinds of nifty inferences from the premises of a valid argument. Your goal in a proof is to, through a series of steps, show that because these rules fit the pattern, because the first parts of these rules fit the patterns you can find in the premises, therefore, the last part of one of these rules follows from those premises. And you keep doing that until you get to the conclusion. And if I haven't said this explicitly yet, once you have made an inference in a proof, you can use that inference as a premise. You add it to your collection of premises. When you're writing any line of a proof, you can draw from any line that came before it. So now, I realize that most of us just have almost no idea whatsoever what we're talking about here. Or we have an idea, but it's just not coming together. You need an example. Let's do an example. We're sort of introducing more information here, saying when you perform a proof, you have to annotate it. You have to show from which step or steps each inference derives and by what rule. But also we're illustrating what the heck is a proof, since some of us still have no idea what a proof is. I say the words, it's a series of steps, and you're thinking, what kind of steps? How do I make these steps? Well, here's how. Here are 4 premises. I don't know that I need to color code this or anything else, but I'm going to make the premises color coded in bold, and I'll put the conclusion in blue italics. So here are 4 premises and the conclusion that we're told follows from them. Our goal is to prove that that conclusion follows. Our premises are if A then B, if B then C, if C then D, and A. 1, premise 1, if A then B, premise 2, if B then C, premise 3, if C then D, premise 4, A, therefore D. Our goal is to show that D follows. And here's a very simple proof that draws from these premises. From premise 1 and premise 4, we get, applying the modus ponens rule, B. It's as simple as I said it was. If P then Q, P therefore Q. That's the modus ponens rule. All we're doing is taking the infallible truth that Q follows from if P then Q and P, and then we're applying that pattern to these specific statements. If A then B, A therefore B. That's it. And now we use that inference to get to our next step. If B then C and B therefore C. So that's the next step of our proof. And with the first step, we show we cite our step. We cite the logic that gets this step, the logic that accomplishes this step. B follows from if A then B and A by the modus ponens rule on premises 1 and 4. And now treating 5 as a premise, that was step 5, but now using step 5 for the next step, step 6, treating 5 as a premise for anything that comes after it. If B then C and B then C, citing again the same rule, modus ponens, but now steps 2 and 5. And then the rest is, at this point, fairly straightforward. If C then D and C are in place in premise 3 and 6. And by modus ponens rule, that gives us D. That's it. Your last step of a proof should equal that conclusion that's been given. Now, proofs might be set up in a different way in a different logic textbook. This is a very standard way of setting them up. I hope you don't see anything much different. But whatever you see, you should see a set of premises and a conclusion that you're told derives from these premises. You just have to show that it derives from the premises. And so you have your information you draw from, and the conclusion you're supposed to demonstrate can be drawn from it. And the rest is the drawing. Draw one step at a time until you get to the conclusion. Now, I think I want to do this proof in a different way. There's often more than one way to do the same proof. Hypothetical syllogism lets us go from if P then Q and if Q then R, then if P then Q and if Q then R, to if P then R. So I'm going to do this proof a bit differently now. I'm going to go for, yes, I'm going to do a hypothetical syllogism on premises 1 and 2. If A then B, and if B then C, therefore if A then C. I'm not trying to have my premises in, not trying to have everything bold and red here in the steps to proof. Okay, so what did I conclude here? I concluded if A then C from premises 1 and 2, if A then B, if B then C. And that's the hypothetical syllogism rule that lets me make that inference. Now, let's see. You might have noticed I just typed this up a bit differently. I said premises 1 and 2 by hypothetical syllogism. In fact, you can also add the word from. In fact, you can spell out as much as you like if it helps, assuming you don't have a teacher who objects to that. When I had my original brief 1, 2 HS or 1, 2 MP, or I guess it would have been 1, 4 MP. All I was saying was that that step of the proof follows from those premises by that rule. So I'm saying the same thing here with a little more information, and I like it. I might keep it. I like having more information here. This will probably help the occasional student of logic. So what's a good next step? We have if A, then C. And we're trying to get to D. What could get us to D? Well, probably these 3 statements are going to get us to D. Probably. Now, how are we going to use them to get to D? There's 2 ways we could try. We can start with 3 and 5 and do another hypothetical syllogism, or we can take 4 and 5 and get to C. And it comes to the same thing. And most of you, I think, could probably already see where this is going if you don't already know. If we do a modus ponens on 4 and 5, we get C. And then we can go directly to the conclusion after that, I believe. That's right. We go to D from 3 and 6 by, again, modus ponens. I'm going to do more hypothetical syllogisms, though. So let's erase some of that. Let's go back to our hypothetical syllogism strategy. If C, then D, if A, then C. If A, then C, and if C, then D. Therefore, if A, then D, which follows from uh, 5 and 3. If A, then C, if C, then D. Therefore, if A, then D, by hypothetical syllogism. And now we go directly to the conclusion, which we can only get by modus ponens. If A, then D, and A, therefore D. So by 6 and 4, from 6 and 4, by modus ponens, we get the conclusion. That's how a proof works, and it's pretty much just that. The rest is just details and more complexities that are meant to help you, meant to help train you in logical thinking. Let me see if there's one other thing I need to mention before we continue. One other thing I should mention is it's good to put the steps, good to put your citations in the right order. And I think different logic teachers will care about this or won't. I think it matters a little bit. I would probably if you were taking my course, you'd get an A- or something on homework if you did everything right, except not put these citations in the right order. So the rule we're citing for modus ponens here is if P, then Q, P, therefore Q. So the pattern that fits on this final step is if A, then D, A, therefore D. So the first bit of modus ponens is the bit with the arrow, the if then. So that's number 6. So mention 6 first in your citations. And the next bit is the antecedent of that if then, the if clause. And that's premise 4. So cite premise 4 next, not first. All right. For anyone who may need it, very brief overview of what we've done so far. A proof is a series of steps by which we demonstrate that the conclusion of an argument follows from its premises. Each step will appeal to some infallible rule. So far, we have 8 rules to work with. In a proof, you will be given, in a proofing exercise on a homework assignment or an exam, you will be given a set of premises and you'll be given a conclusion. And your goal is to show that that conclusion is guaranteed by those premises. You show that by using those rules to appeal to the premises. But once you've made a valid inference, every appeal to a rule is a valid inference, assuming you did it rightly. Every time you apply the rule, you will be making some conclusion from those premises. And every time you do that, that conclusion gets to be used as a premise for the next ones. In other words, we're still building on our intro unit, aren't we? We're still using concepts from the intro unit. These are sub-conclusions. Everything between the premise and the final conclusion of a proof is a sub-conclusion. It's a conclusion with respect to the original premises, but you use it as a premise for everything that comes later. Now, I think the rest I want to cover in this video is just some strategy and good advice. And I think I just want to go over Mike Beatty's rule. This would be Dr. Mike Beatty of Baylor University. I TA'd his logic class, and we were using the Power of Logic, good textbook. And his advice was to work backwards. So now to illustrate, here's a way you could do a proof. By the way, did I explicitly state this in my review? Rewind, pause, interrupt self, rewind just a bit. When you're doing your proof, state some sub-conclusion that follows from your premises until you get to the final conclusion. And state by which infallible rule it follows and from which premises. Okay. So now, I haven't spelled out everything here. I did a bad job. I have to fill this in. Here is an argument. I'll illustrate Beatty's rule of working backwards in a moment. Let's first state what the argument is. I'll go ahead and color code and bold the premises, and then color code and italicize the conclusion. Our premises are premise 1, A or B. Premise 2, if A then C. Premise 3, if B then D. Premise 4, Q. Premise 5, if Q then not A. Conclusion D. So how do you get from this conclusion, from these premises to this conclusion? Well, you could try this. You look at this and you might see that the constructive dilemma rule applies very easily to the first three premises. If A or B, either A or B, if A then C, if B then D, therefore either C or D. Very simple. This applies by constructive dilemma on premises 1, 2, and 3. And then once you have C or D, you should be able to get, actually, I don't know where you go from there. So let's go to what we do have. Q. If Q, then not A. Well, by modus ponens, that allows you to conclude not A. If Q, then not A. Q, therefore not A. Modus ponens on statements 5 and 4 will give you statement 7. And then that was easy enough. We took a simple rule we could apply to the first three statements, the first three premises, and then another simple rule we could apply to the next two. And now we're stuck. How on earth do you get to D from here? I have no idea. So here's what you should do, work backwards. And what I mean by work backwards is this. Take your original argument, keep its color coding if you have any. Take your original argument and look for some way to get to the conclusion from the premises by starting with the conclusion and seeing what in the premises might lead to it. You see what in the premises might lead to it? This conclusion is D. It occurs in premise 3. Premise 3 is if B, then D. So obviously, our last step of the proof is probably going to be a simple modus ponens, if we can just find some way to affirm B. So now working backwards, how are we going to get to B? Where would B come from? We're going to use it on premise 3 once we have it. Use it with premise 3 to get to our conclusion. Where are we going to get B in the first place? Well, we're going to have to get it from A or B. Now, how are we going to get to A or B? Oh, well, it's already in the premise, sorry. We're going to, let's retrace our steps backwards and then proceed. We're trying to get to the conclusion D. We can find D in premise 3. We see from the structure of premise 3 and the conclusion that a modus ponens will give us D from if B, then D, if we can just affirm B. If B, then D, B, therefore D. All we need to do is find a way to affirm B. That's B by itself, just B. So how are we going to affirm B by itself? Probably from here. The other premise that has a B in it is A or B, premise 1. How can we affirm B from A or B? Well, there's one rule that will get that for us. Either A or B not A, therefore B, and that's the disjunctive syllogism rule. This rule, P wedge Q tilde P, therefore Q, or P wedge Q tilde Q, therefore P, that will give us B from our first premise if we can just get a denial of A. Where can we get a denial of A? Where can we get tilde A? Well, maybe here if we could deny C, but let's check somewhere else because I don't know where you can get rid of C from. But here we can get tilde A if we can just affirm Q. How can we affirm Q? Nothing simpler. In other words, working backwards, we should easily enough be able to get to D by a modus ponens on premise 3 if we can just affirm B. How are we going to affirm B? We can get it from premise 1 if we can just deny A. How are we going to deny A? We can deny A using premise 5 if we can just affirm Q. How are we going to affirm Q? Oh, how terribly convenient. It's already there. So now start with that last arrow I just put on the screen. Start with Q. Q, and if Q, then A. In other words, a modus ponens on statements 5 and 4 will give us tilde A. And we're already very much in business. From tilde A and A or B, we now can apply the disjunctive syllogism. So apply disjunctive syllogism to premises 1 and 6, and that gives us B. And then from B, we get D by modus ponens on 3, and we're done. And we're just about done with this video. Now, in my earlier notes, before I started recording today, I had a note to myself to give my rules, my strategies. Beatty's strategy is very good. It will go a long way. So let me see if I can give you one or two other strategic tips before we wrap up this video. And then I think in the next video, we're going to rewind and go through some of this again, maybe all of it again, but more slowly, because I know some people need that. Some of you don't need that. Take a break for a few weeks if you're following this channel. No, 1 week, probably just 1 week. But some people need this. So we're going to go slower, I think, in the next video and do this more simply. But before then, let me see if I can give you 1 or 2 points of strategies to supplement Beatty's advice. And I think I'm not at the top of my game right now, so I'll just give you one piece of strategy. And this is not an infallible rule; it's just a rule of thumb. It will often help you. And the rule of thumb is once you've used a premise, you probably will not need to go back to it. Now, there are cases where you do need to go back to it. So if you get stuck, consider going back to it. But let's pretend we hadn't done this one yet. Let's go back and do it again. Now we concluded we could get to D from premise 3 if we could just affirm B. We could get to an affirmation of B for premise 1 if we could just deny A. We can get to a denial of A from premise 5 if we can just affirm Q, and we can affirm Q from number 4. So then here's what we do. We start there, Q horseshoe tilde A, and Q, therefore, A. Here's another way we could phrase this stuff. It follows by modus ponens on premises 5 and 4, as opposed to this follows from 5 and 4 by modus ponens. Doesn't matter. Doesn't matter a bit. But I hope it's clearer. Do whatever works for you, unless your teacher tells you to do something different. But understand probably whatever your teacher tells you to do for your citations, it'll mean the same thing as this follows from 5 and 4 by modus ponens or whatever. Anyway, so I've now used Q and Q horseshoe tilde A. I've used premises 4 and 5 to get me to premise 6. So probably, if you're doing your proof well, once you use a premise, you don't need to go back to it. And you will probably want to use whatever subconclusion you got from it. So now I'm not going to look at 4 and 5. I am going to look at 1, 2, 3, and 6. So now I've just used this, so I'm probably going to have to use it on something else. Even if I've already forgotten how I'm going to work backwards, once I've gotten this far, Once I work backwards enough to know that I start with 4 and 5, I just start with 4 and 5. I can forget everything else as long as I proceed in a good manner. And a good manner would be A here. Oh, sorry. What a horrible typo. I apologize. Tilde A here. Tilde A is going to get me something useful. Now, I can't use tilde A on number 2 because that would be a fallacy. If A, then C, not A, nothing follows from that, not validly. You'll notice that we don't have, among our inference rules, denying the antecedent, affirming the consequent. We do have modus ponens, modus tollens, because those are good arguments. Those are valid. They're infallible. Denying the antecedent, affirming the consequent are fallacies. Can't use that. So tilde A can only be used usefully at this point on A or B. And what does that give me? Well, it fits perfectly the structure of the disjunctive syllogism pattern. So if A or B, not A, therefore B, by the disjunctive syllogism rule on premises 1 and 6. Or if you want to be meticulous, premise 1 and subconclusion 6, if you like. So now I've used premise 1 and subconclusion 6, and I won't say I've used them up because they're still there, and you never know for sure until you finished a proof that you won't have to go back to one of these premises. There are occasions that call for it, but at least for working through the proof until you figure things out, you can assume probably you don't need to go back to them. Don't scratch them out in your own homework like I'm doing. Just don't. If you're doing your homework electronically and you can scratch them out and then unscratch them out, yeah, sure, whatever, that should be fine. I'm just scratching it out to illustrate. I'm not going back to them in this proof. Okay, so now I have B. And what do I do with B? Well, again, look at premises where you can use that information, and that's premise 3. So now I'm going to use premise 3 and 7 to get to D. And that's it. Suddenly we're done. And we've used premises 1, 3, 4, and 5, and we've used both of our subconclusions. So the general strategy here, just a rule of thumb. Beatty's rule is work backwards, which is very good. And again, it's still also a rule of thumb. You won't always need it, but it's a very good one. And my additional rules of thumb, maybe less universally applicable than Beatty's rule, but still very useful. My rules are, once you use a premise, keep going. You probably usually will not need to go back to it, though there are exceptions. And use what you have. Once you have something in a subconclusion, once you have a step that drives something, look to see a way you can use it. All right, I guess that's it. And is there anything else I needed to say? I think I've forgotten something. It's important. Let's hope I remember it in time to put it in the next video. Thanks for watching. Good luck with proofing. See you next time.